Fundamental problem F12-2 says a ball is thrown vertically upward with a speed of 15 meters per second, and we need to determine the time of flight when it returns to its original position. So since the ball is thrown with a speed of 15 meters per second, we can call this speed v0 for initial velocity, and of course the original position as s0 for initial position. Knowing that, we can now go ahead and write down our givens. So of course we have v0, which we said is 15 meters per second. And then s0, since we aren't given any specific information about position, s0 we can assume as 0 meters. And lastly, we have s2, or position 2, which is also 0 meters, since we're told that the ball returns to the original position. So hence, s2 is essentially equal to s0, which is 0 meters. And so these are all the values we are given. And now we want to know the time the ball takes to return to the original position, so we want to find t. And so how can we do this? Well, first of all, we know that the ball has a velocity, which is of course essentially 15 meters per second. But as it is thrown upwards in the air, what causes it to come back down to its original position? Well, of course, just like any other object, this is gravity. So therefore, this ball will have a constant downward acceleration due to gravity g, which is approximately 9.81 meters per second squared. And once again, this is a constant acceleration, meaning that it does not increase or decrease over time. So now that we have this important piece of information, for constant acceleration, we do have a set of formulae that we can use. So initially, we can go ahead and write down our known values, which are v0, s0, s, which in this case symbolizes s2, and lastly, acceleration a. So from the three constant acceleration formulae, we can simply use position s as a function of time t, which has the formula s equals s0 plus v0 times t plus 1/2 a sub c times t squared. And with a quick recap from my introductory video, this is derived from the integration of the equation ds is equal to v0 plus a sub c times t, where ds is integrated from s0 to some s, and the right side is integrated from 0 to some time t. So now subbing in the known values into this equation, here s is 0 since we said that s symbolizes s2 in this case. So this is 0 is equal to s0, which is also 0, plus 15 times t plus 1/2. And now before writing down the value of a sub c, which is of course constant acceleration, if we assume here upwards as positive, then the value of g will be negative, since of course gravity points in the downward direction, which hence carries a negative acceleration, which is simply negative 9.81, and then that times t squared. So now we can go ahead and simplify down this equation, which hence becomes 0 equals 15t minus 4.905 t squared. And now I'll just rearrange this to have positive 4.905 and then negative 15. So we're left with 4.905 t squared minus 15t is equal to 0, which is of course a quadratic equation. So hence we can go ahead and simply apply the quadratic formula to solve for t. So this is 15 plus or minus the square root of negative 15 squared minus 4 times 4.905 times 0 divided by 2 times 4.905. And of course on the left here, this is what t is equal to. So after putting this into a calculator, we have t1 is equal to 0 and t2 is equal to 3.058. And so from these two values, this is the one that makes sense, since we don't expect the time to be 0. So therefore, Time t will roughly be equal to 3.058 seconds.